Why our solar system is always presented in a 2D disk shape? Well, that's what we're going to explore in today's episode. What's the most popular elementary school project you could think of? Seeds grown from paper? The foam volcano? Whatever it is, I bet that if I ask you to make a list, one of the items that would be on the top of it will be a model of the solar system. If you would recall, these models are basically concentric circles with balls placed somewhere on the circle's circumferences. The balls represent the planets, while the circles represent the orbits. Because of how plain it looks like, one might be tempted to think that this is an oversimplified version of the solar system. I mean, the popular model of the atom is somehow derived from this, right? The exact reason why we call it the planetary model of an atom. And if our star system doesn't really look like that, then I think we did an awful job of naming it, didn't we? Of course, you wouldn't tune into this episode if the answers were that easy, would you? Despite being counterintuitive, the elementary science fair model of the solar system is actually as close to reality as it could get. I know what you think, but that doesn't make sense. We have a three-dimensional space, so naturally, we can expect that every structure in the universe would be in 3D too. Now, I'm not saying that logic isn't right. It does make sense that if we are in a 3D space, then we expect 3D structures. For instance, some stars could experience an extremely strong influence of gravity, causing them to collect together and form a spherical structure that are called globular clusters. They're a common sight in the universe. In fact, in our very own Milky Way galaxy alone, we are bound to find around 150 of these stellar clusters, but they're not the star of the show today. This is all too weird, right? With all the freedom of motion they have, with all the space that is available for them to move about, a lot of heavenly bodies seem to favor moving in a very confined manner. But how and why exactly does this happen? Well, to be able to understand how motion in the universe ends up this way, or at least in the solar system, we need to recall two important concepts in physics. First, we need to relearn angular momentum. I know a lot of our viewers have a pretty strong grasp of a lot of topics in physics, but we here in the channel want to invite more and more people to be interested in science, so for their sake, I'll make a brief walkthrough of what that is. Second, we need to recall how our very own solar system was formed, around 5 billion years ago, back when the sun wasn't even a star yet. Ready? Okay, so here it goes. So angular momentum first. If you know linear momentum, then angular momentum wouldn't be too hard to grasp. Linear momentum is the tendency of an object to move in a straight line. By that logic, we can say that angular momentum is the tendency of an object to rotate. I hope you're not lost so far. Trust me, learning this is really important in understanding the main goal of the video. Now, there are two most fundamentally conserved quantities of motion in the universe. On one hand, we have energy and then momentum on the other. By this logic, we can derive that all momenta are conserved, even the angular one. So okay, angular or rotational momentum is conserved. What does that imply? Say for example, you have a top that's spinning perpetually. It doesn't stop. It just keeps spinning and spinning. So you can perform measurements on it any way you like. Now say for instance, you measure the angular momentum of this spinner at one time. After doing the task, you felt hungry, so you came out for a long lunch, then came back and measured it again. By conservation laws, you want to get about the same value for angular momentum as you did earlier. Angular momentum depends on two factors. First, the distribution of mass in the spinning object, and second, how fast this object spins. Let's relate that with rotational momentums need to be conserved all the time. Since the value of angular momentum is constant because of conservation laws, whatever change in one factor, the other has to compensate. For instance, if the distribution of mass becomes less, say for example the volume of this object decreases, then the rotation has to increase. You can see how this works in ice skaters spinning faster when they draw their hands closer to their bodies. The same works the other way. If the rotation of the object increases, since angular momentum loves to stay constant, the distribution of mass increases. If you know how to make pizza, you would notice that the dough only becomes flat when you make it spin. Can you piece it together now? The answer to why objects in the solar system, or a large number of objects in the universe, seems to favor a flat orbital plane over a volumetric one If you can't yet, don't worry, that's exactly what we're here to learn. The next thing that we need to learn is the formation of our solar system. How exactly are we going to accomplish that? Let's go back about 4.6 billion years to the past, at a time when the sun isn't even a star yet. Back at a very simple time when the materials that would make our own star system home are still swirling about in a large cloud of dust. But before we take a deep dive into that, why don't you send love our way by clicking that like button? Or if you believe we've done awful here, just click on that dislike. Whatever opinion you have is precious to us, as it helps us make better content. Okay, back to the beginning of the solar system. As everything in the universe, our small star-centered family began as a huge cloud of molecular dust. Everything was so simple. Particles are just moving about with respect to a common center of mass. The individual particles in this cloud are not stationary. Due to the effects of the very subtle gravitational force about the common center of gravity, the particles are colliding against one another, causing the cloud to have a spin. Like if you could take a spaceship and observe it from a certain point of view, you're bound to see a spinning cloud. This spin is really slow, like extremely slow, but nonetheless a spin. Then, at some point in the past, we don't really know when exactly, but scientists infer that it most probably happened. A massive supernova took place somewhere near the then developing solar system protocloud, causing it to spin way faster than how it initially goes. Remember the pizza dough analogy earlier? Now the cloud of dust is exposed to this kind of tension. We said earlier that angular momentum is a quality that loves to be conserved, meaning if you measure this quantity at some point in time, you are bound to get a constant value. It doesn't change. So when the cloud of dust experienced energy and increased its rotational speed, it had to compensate. The distribution of mass has to decrease. How exactly does that happen? The particles in the cloud are moving farther and farther apart from their common center of mass. The blob that was the cloud of particles earlier becomes flatter and flatter. And voila, we have a flat proto-cloud disk. As time goes by, the continuous spin from individual clumps inside this disk coalesce to form everything that we see in the solar system. The planets, the comets, dwarf planets, and even the sun. I have to say though, some mathematics suggest that it is possible to describe a cloud spin in 4 dimensions in an attempt to understand it better. However, doing this doesn't result in blobs transforming to plates in the end, so it is most likely an inaccurate description. For the sake of discussion, we can ignore that idea, or maybe we can cover it in another video. Stay tuned to find out. Now, okay, we know that generally most of the objects in the solar system are laid down flat, but what about the anomalous orbits? You know exactly what I'm talking about. The odd brother, and formerly the 9th planet of the solar system, Pluto. The X-planet's orbit is what scientists label as eccentric. No, Pluto's orbit doesn't dress up with a weird fashion sense. Not that kind of eccentric. What they meant by it is that the orbit of this celestial body is tilted by 17 degrees with respect to the orbital plane. Besides that, its orbit is more oval than everybody else. It gets moments when it's really close to the sun, and then it gets moments when it's super far from everybody else. Now okay, so the question in everyone's mind, I guess, is our solar system unique? Is our solar system the only star system in the universe to have a preference for flatness? How about you place your bets in the comment section below? Winner gets to see the next episode. Well, you don't have to look very far to see that it's not just our home system that has a planar orbit. See how the asteroid belts form in the outer regions of the solar system? I'm willing to bet that you're bound to see that they too seem to follow a flat orbit. Okay, maybe not entirely because a torus shape is more appropriate, but they are still lying on the same plane, so to speak. Then let's take for instance Jupiter and Saturn, our planetary family's 2 big brothers. Both of these planets have natural satellites, which are regular, which means they orbit around the planets in a, surprise, surprise, a plane-like orbit. And while we're at the subject, let's talk about Saturn's rings as well. Notice how in the images, the planet looks like a huge ball in the middle of a CD with an unusually large hole? Scientists infer that these rings have formed in the same manner as the regular moons, through the conservation of angular momentum. In fact, when Cassini took an image of it in 1997, it captured a few smaller mini-moons forming inside the rings, which confirms what we already know about planetary and satellite formation. If you travel far enough into space, you are bound to see that our very own Milky Way also appears to be flat in shape. And if you carry on with your travels and approach the galactic center, you are bound to see a supermassive black hole. Considering how massive these objects are, it is with most certainty that you find an accretion disk around it, another flat formation resulting from a combination of forces in 3D space. Although, not saying that accretion disks can only be found in black holes, okay? Practically anything that's massive enough can exhibit accretion disks around them. Usually you find these around developing stars, neutron stars, binary stars that are eating its twin, to name a few. So there we have it. We are hammered by the irony of the universe. With all the freedom of movement that objects are bound to have, most of them still have the tendency to simplify into a flat, two-dimensional shape. But then again, it's not like the objects opted this to happen, right? We learned that with the right amount of gravity and the desire of things in the universe to keep spinning, the outcome is something we can always guess. There's nothing really special in the formation of flat structures. It's just the laws of nature, specifically the conservation laws at work. And isn't that neat? With our pursuit of knowledge, we have arrived at a point where we can describe most of the stuff that's going on, not just on Earth, but in the universe as well, with rules that we arrived at using observations that were initially done on our home planet. I know that's a lot to take in, but let me just say that every day I am extremely amazed, not just by what we see out there in the universe, but the way we mankind arrived at methods to